So this is lecture 27 on linear algebra and eigenvectors. So I assume this is not your first experience or exposure to these ideas. If it is, my apologies. So if A is a matrix, an n by n matrix, and there exists a number, a real number, and a non-zero vector, such that the matrix times the vector is equal to lambda times that same vector, then V is an eigenvector with eigenvalue lambda for the matrix A. All right. Now, first of all, if that's the case, then notice what happens. If that's the case, then AV equal to lambda V is equivalent to A minus lambda times the identity matrix, all times V equal to 0. But the thing is, 0 times this matrix is also 0. So we have that the matrix A minus lambda V does not have the unique solution of 0. It has more than one solution. And if we're working over the real numbers, if you have more than one solution, then to the homogeneous problem, it follows that the matrix inverse does not exist. Because think about this. If the inverse did exist, you could multiply A minus lambda I by the inverse and you'd just get 0 as the only solution, right? So if a non-zero solution exists for the homogeneous problem, it must be that that matrix is non-invertible, which, more to the point, means that the determinant of that matrix, A minus lambda I, must be 0. And in fact, this is why we define the characteristic equation as the determinant of A minus lambda I. This will be a nth order polynomial equation with real coefficients for an n by n matrix. And the solutions to this characteristic equation are called characteristic solutions, and in fact they are eigenvalues. That's the next theorem. Given a n by n matrix, the eigenvalues of A are solutions to the characteristic equation. For each solution, there exists at least one eigenvector corresponding to those solutions. So this is the start of a more complicated story. In fact, for a n by n matrix, there may be no eigenvalues. For example, a 2 by 2 matrix with no eigenvalues would be like a rotation matrix. If you think about a rotation matrix for angle other than 0 or pi, if you rotate all vectors, all non-zero vectors, they never go back to themselves, right? So there's no eigenvalues. There's no eigenvectors for the 2 by 2 matrix cosine, sine, minus sine, cosine for theta, not geometrically identified with 0 or pi. So there do exist matrices with no eigenvalues. And furthermore, the eigenvectors may be insufficient to form an eigenbasis. It turns out that if you can find n linearly independent eigenvectors for a matrix, it means that it's diagonalizable, which is really neat. But, so you're like, well, what happens if it's not diagonalizable? Well, that leads you to study what's called the real Jordan form. And just to give you a flavor for why that's important, if you were to solve this system of differential equations, dr dt equal to AR, well, you can solve that by writing R of t as e to the tar naught, where e to the ta is the so-called matrix exponential, which is defined in terms of the power series, like so. Power series of matrices. You can prove that this series of matrices converges for any matrix because you can show that the matrix norm of the sequence of partial sums is in fact a Cauchy sequence, and as such converges because it's real. But anyway, this does exist, and furthermore, the Jordan form exists for any matrix, and there exists in fact a matrix of Jordan generalized eigenvectors P such that A is P inverse JP, and that's pretty wonderful because then instead of calculating this endless series, you can say e to the ta is in fact e to the P inverse TJP, which you can pull the P inverse and the P out because of the way it works. And exponential TJ, well, that's actually pretty easy to calculate because Jordan forms are simple. Now, we don't need any of this. I'm just telling you, if you don't know about the Jordan form already, it's something you ought to study because it's the part of linear algebra that we don't always get to in the undergraduate course, but it's actually really, really important for applications. And it's the end of a story that you just saw the start of. And there's no reason to not study that as soon as you have some time, because it's really interesting and it's worth studying. I highly recommend looking up the Jordan form and trying to understand it for yourself. If you're interested in that, you want me to give you some, pointers where to look, happy to do it. Just ask me. Now, that said, we don't need all this here, so what we do need is the so-called real spectral theorem. And the real spectral theorem says the following. If the matrix is symmetric, then the eigenvalues of A are real, and in fact, the matrix is orthonormally diagonalizable. Well, what on earth does that mean? Well, let me try to explain. So what this means is, given A transpose is equal to A, in other words, it's symmetric. First of all, the characteristic equation has solutions which are real. These don't have to be distinct, they could be repeated. Number two, the eigenvectors corresponding to those solutions, v1 through vn, can be chosen. They don't automatically come this way, but you can make them this way. Orthonormal. In other words, the dot product of them is either 1 or 0. So these have length 1, and they're all perpendicular. And of course, they're eigenvectors. And what that means then, among other things, is if you make a matrix by gluing those together, first of all, the orthonormality implies that the inverse is the transpose when you study it. And you can calculate that this similarity transformation of the matrix, P inverse AP, is actually P transpose A that. But by properties of matrix multiplication, this A times V1 is AV1, AV2 AVN, which is lambda 1 V1, lambda 2 V2 lambda n Vn, which is this stack. So P transpose is this stack of row vectors times that. But this times that works out to just the diagonal matrix with lambdas in it, because V transpose Vj is delta ij. And so that's really beautiful. And the reason that's beautiful is because of the for us, the application of the Hessian, which is in fact a symmetric matrix. So let's go ahead to that. So if Q is a function from Rn to Rm, and it can be expressed in the formula x transpose Ax for some symmetric matrix A, then Q is what's called a quadratic form. There are more elegant definitions of a quadratic form, but this one suffices for our purposes, all right? Basically, a quadratic form is one which has a linear combination of squares or products of variables that are just at most two variables. So this is a quadratic form, x squared plus 4xy plus 2y squared, or this is a quadratic form, x squared minus y squared plus 7z squared plus 3xy, all right? And for each of these, you can write it as a row vector times a symmetric matrix times a column vector, like that. The thing is, you could also, like, in principle, put a 4 here and a 0 here and spoil the symmetry, but we won't do that because symmetric matrices are awesome. We'll say that the matrix such that, x transpose Ax is Q, is the standard matrix of the quadratic form. This is different than the standard matrix of a linear transformation. Quadratic forms are not linear transformations, in fact. There's something else. So there's more than one thing you can do with a matrix. You don't just have to make a linear transformation. You could make other things. But in any event, here's the theorem. Given a quadratic form, Q, there exist eigencoordinates, x bar 1, x bar 2, x bar n, such that the formula for the quadratic form is given by a weighted sum of squares of the eigencoordinates, lambda 1 x bar 1 squared plus lambda 2 x bar 2 squared, da da da. And in fact, this x bar is nothing more than P transpose x, where P is that matrix of eigenvectors, and we're assuming that they're orthonormal. Here's a proof of the theorem, essentially. It's not quite a proof, it's part of the proof, So I guess I could say approximate proof. Q of x is this, but then we can put in the identity matrix and the identity matrix like that. And then by the property of transpose, this is P transpose x transpose times, well, no, this is just associativity of matrix multiplication there, P transpose x. But P transpose x is x bar, and this is x bar transpose. And P transpose AP is just the diagonal with the eigenvalues, and that is straight up that formula. So here's an example. If you have 2xy, the matrix was 0, 1, 1, 0. That implies that the eigenvalues are minus 1 and 1, which gives you eigenvectors 1, minus 1, and 1, 1, divided by root 2 to make them normal, length 1. And so that means that in terms of the eigencoordinates, we get formula minus x bar 1 squared plus x bar 2 squared. And incidentally, if you were to look at q of xy equal to 1, you may or may not realize that 2xy equal to 1 is a hyperbola. You should immediately see that minus x bar 1 squared plus x bar 2 squared equal to 1 is a hyperbola. So what might be hidden in cross terms becomes exposed in eigencoordinates. Now, I have collected a few more examples from previous tests and homework that I've given in linear algebra. I hope these help you. Certainly, I don't expect you to, do this stuff under much time pressure, I think. But I would like you to be aware of, like, this is how you can work it out, And you can certainly use technology to calculate, like, the 3x3 matrix in your homework. I try to encourage you to do that. So just to go quickly through some of these results. Here I give a quadratic form in R2. I say instructions: find the matrix, find the eigenvalues and the unit length eigenvectors, and find the formula in eigencoordinates, and sketch the graph for q equal to 9. So that's the matrix. The characteristic equation gives me eigenvalues 1 and 3. For 1, I get this eigenvector. For 3, I get that eigenvector. Kind of the same as the one we saw in the previous example, huh? And so the formula, when you work it out in eigencoordinates, is x bar squared plus 3y bar squared. You could, in principle, write this formula down without doing all this. But in any event, if we look at the x bar squared plus 3y bar squared equal to 9, then that is dividing by 9, x bar squared over 9 plus y bar squared over 3. That's an ellipse, right? Which goes from plus or minus 3 in x bar and plus or minus root 3 in y bar, like that. Now, I think I would like to point out here why this is neat, Remark: 2x squared plus 2xy plus 2y squared equal to 9 is not obviously an ellipse, right? I mean, of course, if you plug it into a software and you graph it, then you'll see that. But if you look at this formula, you can immediately recognize that it's an ellipse, right? It's pretty neat. Sorry, I was out of frame. There's the ellipse. The next example, I have, here's the quadratic form. Here's the quadratic form. Corresponding gives you this matrix. So then you can calculate the eigenvalues by the characteristic equation. I get 1 and 9. You can find the orthonormal eigenbasis. Seems like my orthonormal eigenbasis is always the same. It can be something different, I promise. And then with respect to that, the formula in eigencoordinates is x bar squared plus 9y bar squared. All right. Sorry, that seems an awful lot like the previous example. Here's a 3-dimensional one. So here's a quadratic form. In 3 dimensions, we get this matrix A, and I gave the students that eigenvalues 1 and 10 were for A, and so we can find eigenvalues. This one happens to actually have 2 eigenvectors with eigenvalue 1, and so basically the span of these two vectors is the eigenspace. And so like if I want an orthonormal one, I have to run what's called the Gram-Schmidt algorithm on these. And I get this, and of course the original one that. And anyway, after a bit, I calculate this is the orthonormal eigenbasis for A. Now, this is definitely not something I'm planning to, this is not something I'm trying to push with you guys necessarily. I'm just pointing out that this example actually shows you a place where finding the orthonormal basis actually requires some calculation. It exists, right? But just because it exists doesn't mean you can find it right away. But anyway, once you've found it, then this defines the eigencoordinates, which for this one actually look like this. X bar, Y bar, Z bar is actually these given by these formulas here, like that. And if you were to plug those into the formula for the quadratic form, you could show that the quadratic form, when written in terms of the eigencoordinates, is x bar squared plus y bar squared plus 10z bar squared. And I would like to point out that you can write this down as soon as you know that the eigenvalues are 1 and 1 and 10. Like, you don't need to do all this other calculation to see this. All this other calculation finding the eigenbasis is like, you know, just adding texture to your result, if you will. You can write down the formula for the eigencoordinates without actually finding the eigenbasis. That's one of the things I was trying to communicate with my example. Example 3 here is like, I can write down this formula here, and I don't actually have to find this. Like, it's enough to find out the eigenvalues are -1 and 1. That alone tells me that this formula is there. So that's something useful to know. Of course, sometimes it's nice to be able to find the eigenbasis, or the normal eigenbasis, and work it out for other reasons. But anyway, so our principal application of this will be to the Hessian, so that's what's up next. Thanks.